Hello everyone, welcome to our session for today. So we are going to discuss the topic on dependent motion. So these are the objectives of our discussion for today. At the end of the lesson, you should be able to solve dependent motion problems and relates the positions, velocities, and accelerations of the particles undergoing dependent motion. Okay? So here's the application class for applications for this topic. So as you can see here from this picture, so in this setup, so the cable and pulley system shown here can be used to modify the speed of block B. So this is our block B relative to the speed of the motor. So this is the motor. So it is important to relate the various motions in order to determine the power requirements for the motor. Okay, so what is the power requirements of the motor to raise this block and the tension in the cable. Okay, so the tension of the cable to withstand the weight of the block in order for this cable not to break. Okay, now another applications of this dependent motion concept is something like this. So we have here a heavy object to be lifted up to this into this building and with the use of this car. So we have here the rope. Okay, so these are the rope, or this is the rope, and we have the pulley. So we have the pulley here. So rope and pulley arrangements are often used to assist in lifting heavy objects. So an object like this. So the total lifting force required from the truck, okay, it's the truck, depends on the acceleration of the object, which in this case a cabinet. All right. Now, to help us understand this concept class, so let us have this uh, some illustration here. So many kinetics problems, the motion of one object will depend on the motion of another object. So for example, we have here an object A and another object B here. All right. So we have here the distance from the object, no, from this certain point here, and the center of this, let us say, this a pulley is called is A, and the distance also from this part of this object here to the center of this pulley is equal to is B. So let's make this point here as our point of origin, a fixed point. So this is our reference point where our datum are referred to. So this is the datum with respect to this, and also this is the datum with respect to this. And both of them are referred at this point. And we have here the arc from this point to this point. We call it CD, arc CD, and this is the cable. Okay, so we have here the total length of the cable. So as this block moves up or down, this length here remain constant. Okay, so this remains constant. So the blocks in this figure are connected by an inextensible cord, okay, or rope or cord. In this case, we call it cord wrap around a pulley. So this is a pulley. If block A moves downward, so if this block A moves downward, going in this direction along the inclined plane, so this is the inclined plane, block B will move up So what will happen? Block B will move up. So it means that, for example, if you pull this down, so this block B here will go up, or vice versa. If you pull this down, block B will is pulled down, then block A will go up. Okay? So the motion of each block can be related mathematically by defining position coordinates. Okay, so here we are mentioning again position coordinates. So the one that we mentioned in our topic on the relative motion. Okay, you just recall those class. Now, what does it mean? Position coordinates. So the position coordinates is A and is B. Right, so these are the position coordinates with respect to this one, this point. So these are what we call position coordinates. So each coordinate axis is defined from a fixed point. So this is our fixed point, right? Or we call it datum line, datum line, passing to this fixed point. So this is what we call the datum. So this is the reference point when we measure, no, the distance from this block to this, referred to this fixed point. So we call it datum. So this is the datum, this point, and also this point. And this is what we call datum line. All right, so this is what we call datum line. So if the chord has a fixed length, the position coordinates is A and is B are related mathematically by this equation. We have is A, right? So is A, so this one, the length of this from this point here. Okay, it's just like you're measuring this distance. So is A, this is the position coordinates of this block, plus ICD, meaning, sorry, not ICD, but L here means length of this arc CD, plus is B. Okay, so this is equal to LT. LT means total length. In other words, class, we are measuring the total length of the chord here. Okay, so this length is A plus this arc here, arc CD, the length of the chord CD, plus this length SB is equal to the total length of the chord. Okay, so this is how we express this uh, mathematically, no? This position coordinates here, and as well as this one. So here the LT is the total chord length, and LCD is the length of chord passing over arc CD. So this is our arc CD, which is on the poly. All right. So the velocities of blocks A and B, now these blocks A and B, can be related by differentiating the position equation. Okay, so what is that position equation? So this is our position equation, class. This one. This is our position equation. So when we differentiate this one, okay, so when we differentiate this, we will be able to obtain the velocities of blocks A and B. So after differentiation, so we get this derivative of SA, position coordinate SA with respect to time, plus the derivative of this position coordinates block B with respect to time equal to 0. So we didn't include this one because, you know, uh, LCD, the length of the arc CD, is constant. Right? So since that is constant, this one, this is constant. When this moves up and down, this block A or block B, so this length here, length of the arc, is constant. So when you differentiate that one, that's equal to 0. So derivative of the length of arc CD with respect to time is equal to 0. And so do with this one. The total length will not change. So the total length of the chord will not change as this block A and block B moves up or down. So the total length of the chord will not change. So that's constant. Okay, so derivative of constant is equal to 0. So that's why we have this equation after differentiating this position coordinates equation. So we got this derivative of position coordinate of block A with respect to time plus the derivative of the position coordinate of block B with respect to time equal to 0. Or, so in our previous discussion, when you take the derivative of the position, that's become the velocity, right? So when you take the derivative of this, so this is velocity. Okay, derivative of the position is becomes the velocity. So remember when you have s as a function of time, okay, is s as a function of time. When you take the derivative of this s with respect to time or as a function of time, so we have so ds with respect to time. So this becomes f prime of t, right? So f prime of t. And you know that f prime of t or derivative of this is equal to velocity. Okay, so this one is derivative of the position is equal to velocity. So that's why we have here. Um, and then from here we have this becomes uh, velocity of A, block A, then plus velocity of block B equal to 0. So when you transpose this one to the other side, then you'll get V or velocity of block B equal to this one. So this becomes the equation. Okay. So the negative sign indicates that this negative sign here. Okay. So this negative sign. So that negative sign indicates. So what does it indicates? So it indicates that as A moves down, the inclined, as B moves down here, moves down or moves up. So as B moves up the incline, so in this case, the negative sign indicates that as A moves down, so as A moves down, the incline, so meaning positive is A, so this is the positive is A direction moving down. So B moves up the incline, so it moves up the incline. So moving up, that's negative direction. All right. So acceleration can be found by differentiating the velocity expression. So it means if you want to find the acceleration of the movement up or down of this block and this block, so we simply take the derivative of this. So we get the accelerations that we can have for this block A and block B. Okay, so I hope you understand this one, class. Then consider a more complicated example. We have position coordinates is A and is B that are defined from fixed datum lines measured along the direction of motion of black. No? For example, something like this. So compared to the previous illustration, this is a little complex. No? It's more complicated than the first example. So we have here our SB, okay, and we have here our SA. So this is our datum, refer to this center of this poly, and we have this datum line, okay, and this height here is measured as h, that is also referenced to this datum line. This datum line here is just the same as this one. So this is also position coordinates, no, with respect to this point. So these are position coordinates of this block. Okay. So note that SB is only defined the center of the pulley. SB is defined to the center of the pulley above block B. Okay, so it means that above block B, so this is the pulley above block B. Since this block moves with the pulley, so it means that when this pulley moves up, this block also moves up. All right, so H is a constant, so this one is a constant. So while this block moves up or down with the pulley, so this height here remain constant. It will never change because this pulley is fixed. It is fixed, so it won't move up or down. And this pulley is also fixed from here, so it will not go left or right. So this is fixed. So therefore, this height here, whether this block moves up or down, so this height here remains constant. Okay. So the orange colored segments, so this orange colored segments class, so this part, take note that these are the chord, these are the overall or total length of the chords or of the chord. So this colored part here, colored orange, or how do you see it, red or orange, but I see it as orange. Okay, so that's why I put it here orange. And also this part here. So the orange colored segments of the chord remain constant in length during the motion of the blocks. Okay, so this will not change. This color, they are constant actually. Alright, so from this illustration, I just redraw the illustration class and transferred it on the left side of the slide. So we can explain it further in the right side. So the position coordinates are related by the equation. So these are the position coordinates, SB and SA. So these position coordinates are related by the equation. 2 is B, meaning twice is B plus H plus is A equal to L. L is the total length of the chord. The total length of the chord. So 2 is B. So why 2 is B? Because we have here is B. So this length is B and this is twice because we have this length and this length. So that's why we have twice. Alright? So these are the length that varies. Why I said it varies because when the pulley goes down, okay, when this block moves to the left or to the right. So for example, if this block A moves to the left, what will happen? So the cord will be stretched, right? Because this block holds this block at this position. So when this block moves, so the blocks go down with the pulley, or yes, with the pulley, so will go down. So it means that this SB is variable. Okay, this height will vary. This height will vary, and take note that this height or length of the cord and this length, they are just the same. So that's why we have twice, no, this total length of this length and this length. So you can write it at twice, no, two times is B, then plus the height, this height, plus this height, okay, plus H, then plus this length, position coordinate, equal to I, where I is, what is I? So this part I is the length minus this colored. Okay, so our I here, sorry, not I, L. Our L here is the total chord length minus the length of the orange segment. So total chord length minus this length, this length, this length, and this length. So the equation that we can establish Now the position coordinates equation is something like this. That 2 is B plus H plus is A, or position of block A, position of block B equal to I. Okay, so I hope you have followed that one, class. So since L, sorry, this is not I, huh? I missed this one. This is L, no? Stands for the length. Since L and H remain constant during the motion, the velocities and acceleration can be related by two successive time derivatives. Okay, so you take the derivative of this, you get the velocity, and then take the derivative again. Whatever is the result after differentiating this one is, or after differentiating this equation, position coordinate equation, we'll get the velocity. And when you take the derivative of the result of that, meaning the velocity, when you take the velocity of uh, that we have obtained from differentiating this equation, so we get the accelerations. Okay, so um, since L and H remain constant during the motion, so the velocities and accelerations can be related by the two successive time derivatives, and we'll get this result. So when you take the derivative of this, so derivative of constant 2 is constant, so you just take the derivative of SB. So derivative of SB with respect to time, so we have the VV. So it's something like this, class. So since this is constant, okay, so you just twice the constant, so derivative of constant, which is no, sorry, twice the derivative of SB. So we just derivative of SB, sorry, so we have the SB here. Okay, so position of block B. So when you take the derivative of this with respect to time, so the result becomes, we have 2 times, so we know that derivative of S is equal to V. V, so stands for velocity, and the V here is the block, so twice velocity of the block. So that's why we have here twice the velocity of block, so twice the velocity of block. H is constant, so derivative of constant is 0. Derivative of constant H with respect to time, since H is constant, uh, whether the block B moves up or down, so H become will not change, so that's constant. So derivative of constant is equal to 0. Okay, and sorry, L, L is constant as well. Okay, so derivative of constant is also equal to 0. So derivative of L with respect to time is also equal to 0. So that's why our equation becomes, so this becomes 2 VB, I mean twice the velocity of block B, then derivative of this, so derivative of SA, derivative of SA with respect to time, so that is our velocity of block A. Okay, so this is our velocity of block A. So we have as a result here of our differentiation, this is 2, okay, 2VV, this one, then plus this one, okay, and then you equal to 0. When you transpose VA, velocity of block A, to the right, so you transpose that to the right, okay, we get the result here, 2 or twice the velocity of block B equal to the negative of the velocity of block A. And when you take the derivative of this, then you get the acceleration. So that is still twice a b acceleration of block B equal to negative of acceleration of block A. Okay, so that's the result after differentiation class. So when block B moves downward, okay, so when this one moves downward, so what will happen? It will be pulled, right? It will be pulled. So when block B moves downward, that is the positive is B, meaning this is B here, positive. Uh, so block A moves to the left. So this block A moves to the left, so it will be in this direction. So the movement will be in this direction. So it means that when block B moves downward, so when this block B moves downward, so the movement of this block A is to the left. So that is negative is A. So this one negative. So when this one, the position becomes negative because it goes to the left. Okay, so that's our convention class, sign convention for this. So remember to be consistent with the sign convention. So when we consider movement of the block downward as positive, and this movement to the left also as negative, then we have to be consistent. Meaning, if you move the block B upward, okay, so when you move the block B upward, okay, let me change the color here. Okay, so when this block moves upward, so what will happen? So the this block B will goes this way. Or when you pull this block A to the right, then this will go up. Okay, so this will go up. Block B will go up. So if you consider moving to the right as positive, okay, if this is positive, then this one, this is negative. So that is our convention class. We have to be consistent. So if you consider that when block B moves down, meaning when this block is moved to the left, and we consider that as negative. Now when you consider that as, okay, let me change this color back to red. Okay, so when we move this block to the left, which is negative, and then this block goes down, which we consider as positive. So we have to be consistent of this convention class. So that when we pull this block to the right, so this one goes in the opposite direction, which is going up. So this time this is negative. So this is what is meant by consistent with the sign convention. Okay. Now, procedures for analysis. So how to solve problems that involve dependent motions. So these are the procedures class for our analysis. So first, we define position coordinates from fixed datum lines along the path of each particle. Okay, so we have to define first the position coordinates from fixed datum lines along the path of each particle, and then after that different datum lines can be used for each particle. So each particle can use that datum lines. And relate the position coordinates to the chord length. Okay, so relate the position coordinates to the chord length. Segments of chord that do not change in length during the motion may be left out. Okay, so if they're not going to change, so you may not include it in your establishing the relationship of the position coordinates because they are constant. Anyway, after all, the constant when you differentiate that becomes zero. So you may leave that. No, it's okay not to include them. So if a system contains more than one chord, so relate the position of a point on one chord to a point on another chord. Then separate equations are written for each chord. Then after all this procedure, you have to differentiate, no? Differentiate the position coordinates equation, or differentiate the position coordinate equation or equations to relate velocities and accelerations. Then keep track of the signs. All right. So that's all for the introductory part. Yes, I'll end this video, and I want you to watch the next video for our example. So thank you very much. See you on our next video. Bye.